Okay, so my topic today is challenges introduced by new technologies like to color science. Okay, so a little bit introduction about my university. Okay, so we are Hong Kong Polytechnic University, and which is actually located very close to the center of Hong Kong. And so I'm associate professor here and doing a lot of research related to color and lighting. And we also have very famous textile like research center or the institute here. And we have professors who is also like very famous for color of textiles. Okay, and we collaborate like sometimes on some projects. And oops, yes, okay. So my own research like area, okay, like my so during my PhD, my main research was actually looking at like the physical world, okay, and I mainly focus on the lighting systems. So in other words, how the human beings are actually perceiving the luminous like environment, and which is like somehow like related to color and color rendering. So that was my research expertise when I was still a PhD student. And then after I graduated and then I came to PolyU and I started to expand my research into more fundamental like color science, okay, including like color management, color appearance models. And recently we have been working on like metaverse, okay, so virtual reality, augmented reality, and also the mixed reality like quite often. So that's the reason I have been so knowing like Kaida and also like Ronnie Law for a couple years, and we also work together on some projects. Okay, so I'll start my talk, okay, from pretty fundamental things. So we talk about color, or most of the time we actually talk about the light color. So which means we are talking about so the color appearance of the illumination. And we all know like fundamental like physics. So color is actually, or light is actually a type of the radiation. So we use a two-dimensional plot, spectral power distribution to describe that. So the horizontal axis is talking about the wavelengths. More specifically, we mainly care about the visible like wavelengths. Okay, and then the vertical axis, we mainly care about the radiation and the power. But this is mainly like related to lighting. And for the surface color industry, so we always care about the color of the object. And when we talk about the color of the object, we are actually talking about the property or the characteristics of the object. So because for most of the objects we see in daily life, they are not glowing or they do not emit the light themselves. Okay, they only reflect light. So we call this apple is a red apple. So the main reason is it has a very good so it has a very good ability to reflect the red colors or the wavelengths like related to red colors, and therefore the rest of the wavelengths or the radiation in the rest of the like the wavelengths, they will be absorbed. So that's what we always call the color of the object. So we also use a two-dimensional plot. Okay, so the horizontal axis is the wavelength, and then the vertical axis is the reflectance factor. So the higher the reflectance factor, which means it will reflect higher or greater amount of the radiation in that specific wavelength. So that's the object color, but actually, like the color we see is actually is an interaction between the light color and also the object. So in other words, we use the spectral power distribution to times the spectral reflectance distribution, and then that's the final product that goes into our eyes. Yeah, so that's the final light that goes into our eyes, and so this is where we are talking about so the starting of the radiation in our eyes. Okay, so this is what we call the perceived color. Okay, so this should be spectral power distribution to times the spectral reflectance the spectral reflectance distribution. So based on here, we know like the color we see is dependent on both the illumination and also the object. But we also know that so the colors we see is not isolated from the background or from the viewing condition. Okay, so for example here, like the two squares at the center. So even though if we use a meter to measure their XYZ or to measure their tri-stimulus values, okay, so they will be the same. But very obviously, our perception will tell us they are not the same. Okay, so the color appearance are not the same. So in other words, the perceived color appearance is also affected by the viewing condition. Okay. So this is how so we start to characterize or we care how we can specify the color of the stimuli, and also we're trying to use like so the studies and to help the real applications. And this is actually like the history or kind of the development of the color science. Okay, so at the beginning, we only care about color match. So in other words, under the same viewing condition, so whether the two colors will match in appearance. And then we care about the color difference. So if they don't match, and then how we can characterize the color difference so that we can know, so what's the tolerance or what's kind of the specs we can use on the production line. And then finally, so this is like related to the cross-media color reproduction. We want to like more objectively to characterize, so what is the color appearance, or to characterize like so the different color attributes using so the different models. So this is kind of the history. And then in the color science, actually we have different models, or we use different, so we developed the different tools. Okay, so for color match, so we are actually talking about the color matching functions, or we use the tri-stimulus values. And then to characterize the color difference, so we have like the uniform color space and also the color difference formula. So we try to use a numerical value to quantify the color difference. And then for the color appearance, we have the color appearance model. So the input is still the tri-stimulus values with the viewing condition, and then the output will be the numerical values to characterize the different color attributes. And this is kind of the things like all the color scientists have been working on. And then if we look back, like the applications that's mainly related to the color science is actually mainly focused on the conventional like technologies. Or in other words, we're mainly trying to characterize the color of the fabrics, the textiles, and also for the printing. So for printing and also the painting. And then for these different industries, we are mainly focused on the surface color industry. Okay, so in other words, like the object or the colors will not emit the light themselves. Okay, we only trying to look at, so if we put the surface color under certain illumination, so how the color will be. And then we typically like put these color samples or the color checkers in a standard like viewing booth. So which means we always have standard lighting condition. Okay, so which is mainly include like A source, D65, and also like the fluorescent tubes. Okay, so we fix the lighting conditions, and most of them, they are conventional light sources. And then, so for the object, so as I said, we mainly focus on the reflective surface colors. So which means they don't emit light. Okay, they only reflect the light. And then when we specify the colors, we always have a standard viewing condition, so which is the viewing booth. Okay, so we have kind of like 500 lux to 1,000 lux, so such a light level, and with the neutral like background. So everything has been standard. And this has actually like motivated us to carry a lot of experiment to quantify the color match, the color difference, and also the color appearance. But actually, so in recent years, like because we have like better like systems, or we have like better technologies, we actually like for the lighting, for the objects, and also for the viewing conditions, we are actually having more and more like complicated conditions. Now, for example, for the lighting, we are no longer only using we no longer only use the conventional light sources. We start to have the OLED and also the LED sources, so whose spectrum is more narrow kind of the distribution. And then for the object, we are not only looking at the reflective surface colors, we also care about like displays and also like these AR, VR like conditions. So we start to focus on the self-luminance like devices. And then for the viewing conditions, we no longer put like the colors in the standard viewing booth, and we start to have like more complicated conditions. For example, like the non-uniform like lighting conditions in terms of the intensity and also in terms of the white point or the color of the lighting. So these are the complicated conditions. Now, when we have these new conditions or we have these new technologies coming, we have to look back to these three different like perspectives about the color science. So whether we can still use the conventional method to characterize the color match for the new sources, and whether the color difference like metric or the uniform color space is still valid like for these like new devices, and also for the color appearance models, whether we can still use that for the complicated viewing conditions. And this is actually like most of my research have been focusing on. So we start from the color match. Okay, so this is, I think most of the people, so we already know that, so that's a color matching like experiment have been carried out like almost 100 years ago. So we use RGB, like 3 different colors to create a match so that we can derive the color matching function. And this set of the color matching function has been working pretty well in the past like 90 or 80 years. But actually, like due to the development of the new technologies, we start to find there are a lot of weakness for the CIE 1931 color matching functions. And then, so in 2006 and also like in 2015, CIE published like 2 new documents, and then they are proposing 2 new sets of the color matching functions. Okay, we know it's a CIE, so the CIE 2006 2 degree, and also the CIE 2006 10 degree. And if we compare like these two with the conventional ones, like the CIE 1931 and also the 64, and we know the major differences we have is actually in the short wavelengths. So which means like for the conventional, so the CIE 1931, it actually underestimates like the contributions from the short wavelengths. But still, we don't know so whether these two new set of the functions work well or not. And then I start to look at this problem like because we start to realize that with the development of the display technologies, so we're trying to include more and more colors, okay, from the display. So in other words, we want to push the gamut area of the display. And if we want to have a larger gamut area, we have to put the RGB primaries to be closer to the spectrum locus. So which means like the spectral power distribution will be much narrower for these larger gamut displays. And then if that's the case, it's actually we find it's introduced a lot of the problems. Now, for example, like this image, so even though we know like the cameras cannot really capture what we see in real case, but it actually shows the difference. Okay, so all of these like different displays, we actually calibrated them into the same chromaticity or the same CIE, like so the CIE XY like coordinates. But very obviously, like so no matter like based on this image or based on our perception, we can see very obvious like color differences. And this actually tells us that something is wrong with the color matching functions. And if we want to calibrate the displays like to the same color. And this is especially more serious for white colors. Okay, so because for the white colors, it's actually happening in the middle of the chromaticity diagram, and then like we have like small differences for each wavelength, and then if we add them together, and it can create a very obvious difference. And then for the red colors, so for here you can see it's not so obvious. So that's the reason like the white point calibration is pretty important for the display industry. And then for this, we actually carried out like 2 experiments and mainly trying to see, so if we have an OLED display with an LCD display, so whether the color matching function will really introduce some problems. Okay, so in this experiment, we actually carry out is the color matching task. And we use one reference display, so which is an OLED display. Okay, so its gamut is pretty large, close to P3. So the P3 like a gamut. And then for the test, for the test, we have 4 different displays. One is the LCD, and the other 3 are the OLEDs. But all of these OLEDs, they actually coming from different suppliers. And then, so this image is actually showing the spectral power distribution for these 5 different displays. Okay, so you can see, so very obviously, there are some differences in their spectral power distribution in terms of the peak wavelengths and also like the width of the of the spectral shape. And if we plot like the chromaticity coordinates of the primaries of these 5 different displays, and you can see that there are some differences in the blue and then some differences in the green. But for the red, like their chromaticity was pretty close. But that actually does not affect our experimental results. And in order to see whether they will actually make a difference, we carry out the color matching experiment. And we're trying to maximize the differences caused by these different primaries in terms of our cone photoreceptors. So we built like 2 different apparatuses. And then for the first one, so it's actually a viewing booth, and then we have 2 openings at the back so that we can put 2 displays like behind the viewing booth. So you can see that in the experiment, like these 2 squares are actually coming from the displays. And then, so because of such a setup, so the 2 like tasks, so the 2 stimulus, they are not like next to each other. So it actually created a little bit of a little bit of problems when they created the when the observers were doing the color match. And then for this for this setup, like the field of view of each display was pretty small, only 4.8 like degree, so which is like kind of not very similar to the real conditions. And then in order to make the color match to be better, and then also to make it to be more similar to the real condition, we carefully build another like system. And then in this system, so you can see that the front side is a viewing like hole or the viewing opening, and then we have one opening at the top and the other opening at the back, and we have a 45-degree mirror here. So which means we can put one display here and then one display here, so that from the front side, we can actually see these 2 displays, they are next to each other, okay? And then, so the boundary like between them is very, very small. So the color match was actually pretty accurate for different observers. And then such an opening like at the front was actually creating a field of view of 20.2 degree. so which was more similar to the real usage conditions to the users. And then, as I said, we're trying to maximize the effect of different the spectral power distribution on our cone photoreceptor. So we carefully choose 6 different stimulus for color matching. So in the left figure, so you can actually see that we convert the chromaticity diagram into a cone space. So the horizontal is the air cone, and then the vertical is the S cone. And then you can see these green dots are actually showing the stimulus we use for the color match. So for this one and this one, so you can see that they actually introduce the same S cone, but actually they have very large difference to the excitation of the air cone. And then for this one and this one, so you can see that their air cone excitation is the same, but the S cone has a very large difference. And then for these 4, and you can see that the air and the S, both of them, they are changing at the same time. So that's the reason we selected the 6. And then if we put them back into the chromaticity diagram, and you can see that, so these are the distributions of the 6 chromaticity we used for the color match produced by the reference displays. So this one is actually so it's a white color, and then for these 5, for the rest of the 5, they're actually kind of more saturated or more chromatic. So based on this setup, we actually, so as I said, we make the color match to be very, very accurate. And as what we always do in psychophysical experiments, we introduce the repeated the repeated adjustment. In other words, for the same reference, we will ask each observer to make two match, and then we're trying to see whether the 2 match or the 2 repeated matches, they actually have very similar results. Okay, so these 4 figures are actually showing such a result, and you can see that. So when using the display A as a test, so on average, so the 50 observers, the 2 repeated the 2 repeated adjustments, the delta U prime V prime, so was actually 0.0023 units, and this is actually half of the just a noticeable color difference. And then even for display B, C and D, and you can see that it's pretty stable. So in other words, display was actually not introducing any problem for the intra-observer variations, and all the intra-observer variations were actually very, very small. So which means the experiment setup and also the procedure was actually pretty reliable. And then we just look at the results. Okay, I'm only showing the result for the larger field of view. Now for each of these figures, so it is actually showing the results we calculated using these 4 standard CIE color matching functions. And then on each diagram, you can see we have 6 different colors. Okay, so 1, 2, 3, 4, 5, 6. So these are showing these 6 different reference stimulus produced by the reference display, so which was an OLED. And then, so the red point, okay, so at the center, so it's not so clear, but at the center, so the red point is showing the chromaticity of the reference display. And then, so for the 4 different colors, and so 4 different colors, so they are actually showing the results of the chromaticities adjusted by the observer using each of the 4 test displays to create a match. And then the circles or the ellipses, they are actually showing the 95% of the confidence interval of all the match. So which means if our color matching function was very accurate, so all the chromaticities adjusted by the observers, they should very close to each other, and then also close to the red points. So which means the display did not introduce any problem. And then the smaller the size of the circle or the ellipses, so which means the smaller the differences between different observers. And then for here, so you can see that when we use different color matching functions, in general, none of them work pretty well. Okay, and we find mismatch really happens. So in other words, when we want to create a match, so we have to have different chromaticities to introduce a visually color match. But if the chromaticities they match, but actually the colors will be very different. And then the most important thing we can see here is actually the mismatch actually depends on the colors we are talking about. Now for number 1 and number 2, so this is kind of the red color, and then this is kind of the green color. The differences introduced by the different displays was actually pretty small. But for number 6, so which is actually close to the white point, there's very obvious difference for the purple cycle, so which is the LCD display. So in other words, if we use OLED display with the LCD display, we want to make the colors to be seen or to be viewed to be the same. then their chromaticity will be very different. And put it in the other way, if the chromaticities are the same, then the color differences will be very obvious. So that's for the number 6 of the color stimuli. And then for 3 and 5, so these are kind of the blue and the purple. And you can see that the size of the circle was much larger in comparison to 6. And also like the center of these different circles, they actually have very, so they actually have very obvious like, so the shift, okay, for the blue and also for the purple colors. So which means that for the blue colors, we will have more serious problems if we calibrated the display using the using these like standard CIE color matching functions. Okay, and then so we put so we actually change like this so these 4 figures into a better way. So in other words, we move so the red dot or the chromaticity of the reference into the center, and then we are mainly looking at the shift. Now, if we put it in this way, it's much easier for us to make the comparison. Okay, so 1 and 2, so these are the red and also the green colors. Now for 3 and so for 3 and 5, so these are actually the blue and the purple colors. And you can see that the size of the ellipsis was very large in comparison like to 1 and 2. And then for number 6, so this is actually the white point. And then in particular, you can see that for the white point, like so the purple circle, so which is actually display A, so it was an LCD display, and you can see that the center of this circle was actually shifted in comparison to the to the chromaticity of the reference display, and which means that if we are using CIE 1931 color matching function to calibrate the OLED display with the LCD display, and then the OLED display will have very obvious like green tint. And I believe this is the phenomena so many of you may already experience when you are looking at an OLED display. So it's kind of like a little bit like a green tint or the green shift. So which means CIE 1931 is really introducing the problem for OLED display. So if we calibrate the display using this set of a function. And then the other thing you can see that even though we have like newer color matching functions like the 2006, but actually we are not making a lot of improvement. In other words, like the size of the circle and also like the size of the shift is not like significantly reduced in comparison to the CIE 1931 and also the CIE 1964. So which means still the CIE 2006 the color matching functions did not have a better performance. Okay, and this is actually the things we actually need to look at for these modern display systems. In particular, if we are going to have even larger like display gamut, so which means like the spectral composition of the display primaries is going to be much narrower, and then we will have more serious problems. And also, so because in the experiment we have 2 different like field of view. So in the first experiment it was like 4.6, and then in the second one was 20.2. And then these standard CIE color matching functions were designed for different field of view, and we are trying to see whether the experiments like a field of view and also the field of view for the color matching functions like really matter. So we make such a comparison. Okay, so the horizontal axis was the results like for the first experiment, so the smaller field of view, and then the vertical axis was actually for the larger field of view. Now for different colors is actually showing the delta U prime V prime, the chromaticity like differences. So using these 4 color matching functions, and then different shape is actually talking about different color of the color match. Okay, and then you can see that all the points is actually so it's kind of like randomly distributed across this diagonal line. So which means we are not saying there's a big differences like between different field of view and big differences like between different color matching functions. So in general speaking, color matching function, the field of view does not really making the right prediction for the experiment like field of view. So this is the thing that we find. So to conclude this experiment, so we are actually finding that the current color matching function still cannot accurately characterize the color match or the color mismatch. And then the observable mechanism will become more important when we start to have the narrow band like spectra for the displays. So this is the color match. And then so we mentioned that so the spectral composition will affect the color match, but actually the spectral composition will also affect the color appearance of the object. So this is what we call the color rendering. And then these are the color these are the spectral power distribution for conventional light sources, and you can see that so they generally have the continuous spectrum. And then these 2, they are actually the spectral power distribution for LED sources. So you can see that we can actually make the spectral compositions to be much narrower, or to make the spectral power distribution to be continuous in comparison to the conventional sources. And this actually introduced a lot of the problems in color rendering. And now, for example, so for these two sets of the image, and you can see that even though in general speaking, the color of the boost was actually pretty similar. Okay, you see a little bit difference. So this is because like the cameras is not really doing a good job. But if you're looking at like these like two settings like in person, like you will notice that like the white color or the neutral color does not change doesn't change too much. But very obviously, so you can see that these red colors or kind of the ring, and also the green colors or the orange colors, they really change. So in other words, the spectral composition will really change the color appearance of the object. And based on this, I actually carry out a lot of experiments and trying to see how the spectral composition affects the color rendering for different applications. Okay, so because for different applications, we have different light levels, we have different kind of the objective, and we are actually making different like evaluations or the judgment. And I just want to talk about like the museum setting. So because the museum setting is actually, we have very, very low light level trying to protect these artwork. And this actually introduced some problems. Now, for example, this is the color appearance of an artwork in the normal light level. So you can see all different colors pretty well. But if we reduce the light level to 20 lux, so it will actually make the colors to be washed out. Okay, this is actually because the human visual sensitivity will reduce under the dim light level. And if that happens, we can actually do something to change the color appearance of this artwork by using the spectral power distribution that can increase the chroma level of these different objects on the painting. So in other words, even though we dim the light level, but we can do something to make the artwork to appear more saturated, so that we are not making the composition. So we are making the composition of the reduced color appearance at the low light level. And based on this, I actually want to look at how the color appearance will actually change in the different light levels and how we should specify the color rendering ability of the light source in the different light levels. So we run this experiment. Was actually pretty easy, but we spent a lot of time trying to design the spectral power distribution of the light sources. Okay, so we have 9 different sources, and we use the spectral tunable source to produce these 9 different sources. And we use RG. Okay, RG is actually a metric that we developed in this IES TM30 like system. So this is actually talking about the ability of the light source to render or to increase the saturation of the object. So the larger the value, so which means the colors will become more saturated, okay? And then these 9 different sources, their RG is between 100 and 120. So 100 is kind of the reference, okay? So which means we have a higher, so for these different spectral compositions, we are actually increase its ability to increase the saturation of the object. And then we want to look at the trade-off like between the color gamut or the saturation with the light level. Okay, and we run the experiment in 2 different sessions. Now, the first session, we mainly look at low light level. We started from 20 lux all the way to 480 lux. Okay, 480 is a typical interior lighting application, and 20 is kind of the lowest light level you will experience in museum. Okay, and so that we can make the protection of the artwork. Now, in the second session, we actually look at from 200 lux all the way to 1500 lux. Okay, which is pretty high, and no past experiment was actually looking at such a high light level. Then the experiment was pretty easy. Okay, we gave the control to switch the lighting condition or to switch the spectral composition to the observer, and then they can switch back and forth between like these 9 different spectral compositions and choose the one that can make the artwork to be the most preferred. Okay, so which means that under 20 lux they will experience a 2 minutes. So they actually experience the 2-minute like adaptation, and then they switch like among these 9 different spectral compositions and say, okay, I prefer the artwork under this SPD. Okay, and then we recorded such judgment. So we repeated such a procedure under each light level, and then we take the average of all the RG values like selected by the observer. So this is the results. Okay, so the horizontal axis is showing the light level. Okay, this is only showing from 20 lux to 480 lux. And then the left side, the axis is actually showing the average RG value. So again, the higher the value, which means the higher the saturation, the colors will appear in this light source. And you can see that when the light level was increasing, so the selected RG was decreasing. Okay, we only look at the black curve. Now for the red and also for the blue curve, okay, these are showing the ability of the source to increase the saturation of red colors. So this was actually purposely like designed. So because you can see this artwork contains a lot of the warm colors. Okay, and then you can see that they are actually prefer to have the saturation of the red to be lower and the higher light level, okay, from 0 to 500. And put it in the other way, if we reduce the light level, they actually prefer the saturation to be higher. Okay, so this is actually we can do that if we dim the light level, but we try to increase the saturation to make the colors to be more preferred. And this is only looking at the lower side of the experiment. Then then for the higher side, okay, we start from 200 lux and all the way to 15,000 lux. And then you can see that we still have such a trend. Okay, when the light level was increasing, we actually do not want to have higher saturations. And more importantly, that you can see that when the light level was 15,000 lux, people don't want to have any saturation enhancement. So because the average RG value was close to 100, so which was actually the reference. So because in a lot of the past studies, we find people prefer to have more saturated colors, but actually we think these are actually coming from the reduced light level that we use in the typical conditions. But if we show these colors in the daylight, and people don't want to have a higher chroma level or the saturation. So this is actually showing the higher end. And now if we combine the two sessions into like one figure, okay, you can see that they actually can form a very good like the regression line. But we actually have a lot of data points. They are clustered here. And then in order to show such a difference, and we actually change the horizontal axis from illuminance lux into the logarithm of the illuminance. Then you can see that we from the 20 lux all the way to 15,000 lux. And actually we have a very good like relationship with the RG value and also the light level. So which means this actually supports our hypothesis that higher light level, we want to have a lower level of the chroma. In other words, so for the lower light level, we want to increase the chroma level. So based on this like experiment, we find like in the past studies, we actually only have a very limited light levels. Okay, typically we only look at 200 lux to 500 lux for typical interior applications. But if we have a much lower light level, we can actually, or the human beings prefer a higher chroma enhancement. And on the other hand, if we have very high light levels, we don't want to have any chroma enhancement. And this is actually talking about the daylight condition. And based on this experiment, we actually carry out a more kind of the standard color science experiment, so the color matching experiment under such a hypnoscopic viewing condition. And we try to test whether our existing color appearance model can really predict the color appearance under extremely high light level, or in other words, 15,000 lux. And we find like the color appearance model cannot do that. Or in other words, so the CIE Camo 2 still need to have some modification. So the CIE Camo 2 still needs some modifications to be applied for the highlight level. Okay, so this was because like the existing color appearance model was actually only based on the data sets we collected under the normal light level conditions. And then, so finally, I want to talk about so it's more related to HDR or still the color appearance model. Okay, so when we trying to capture like the real environment and then we show on the display, and we have to do some like image processing or the color like management. And this is mainly because like the color or the range of the colors and also the range of the light levels in the real condition is much wider in comparison to the range we can see on the display. Okay, and then so that includes both of the luminance and also the color range or the chroma level. Okay, and so these are actually like the image I took with my iPhone. Okay, so this is the viewing booth, and then behind the viewing booth we have a very high brightness LEDs to shine on this hole or to shine on this opening. And then on the left image, so we are switching off the HDR. The capture or the HDR like display like mode, and you can see that the colors is not so good. So you can imagine that if we have very bright like a blue color, okay, it should appear kind of like a very crystal blue, but actually this is not the case. But if we turn on the HDR, now you can see that the color seems to be right. But if you compare this color with its like reflection from this wall, okay, there's a very obvious color differences here, and same like appears like to these two. Okay, if we only like capture this viewing booth, okay, you can see all different colors like pretty clearly. Okay, they have the shadow, they have lower lightness. But if we are actually capturing like this booth with a dark booth and turn on the HDR mode, and you can see that the colors is not so realistic. So because we compress the light level or we compress the contrast, but we are not making the adjustment of the chromas very accurately. So the colors appear to be like flat. Okay, they don't have the shadows. So that's the reason we are looking at such an HDR condition like very seriously. And then these conditions were not like looked at in the past. So because we don't really have the capability to reproduce these different conditions. Now to reproduce like the HDR conditions, okay, so the typical thing we do, first step is a tone mapping. Okay, we basically compress the luminance like channel and trying to make the luminance like channel can be shown like very accurately on the display, so that we need to have a UCS or we need to have a uniform color space so that we can actually only compress the luminance like channel or along this lightness axis. And then the second step is we need to adjust the saturation. Okay, so that we maintain the lightness and we only increase the chroma or we decrease the chroma. So this is actually the typical thing we do in the process of the ISP pipeline. So which means that we want to have such a very good color space so that we can process the lightness and also to process the chroma like separately. So we want to have the independence between the lightness and also the chrominess so that we can adjust the colors very good. And you can see that when we're talking about the lightness compression, okay, and also to adjust the saturation, one of the things we are missing here is if the colors is actually a neutral color, so we don't have the saturation, right? So which means we only compress the lightness and we don't want to change the saturation anymore. So which means we want to have this vertical axis to be perpendicular to the chrominance like plane, so that's for neutral colors, we only adjust its luminance. And based on this, we're actually looking at how the existing like models can really do that. So we run this experiment. Okay, this is a viewing booth, and then behind this like neutral color patch, we put an iPad. So the center like square is actually coming from the iPad. Okay, we make the iPad to be very bright. And then for these 8 different colors, they are actually like the Moncel like samples. So we use like such a setup to create an HDR condition. In other words, this stimulus is kind of very bright in comparison to the luminance of a diffuse white and under the same condition. Okay, so that's not the standard like SDR condition, it's an HDR. And then we run this experiment with different setup. Okay, we have 13 different adapting conditions. Okay, one is dark condition. Okay, in other words, there's no ambient light so in this booth, you only see this patch coming from the display. Okay, it's kind of the unrelated color. And then for the other 12 conditions, okay, we have 3 adapting luminance with 4 adapting CCT. Okay, it's cross. So it's like a 3x4 design. So the 3 adapting luminance is 10, 50, and 115. Okay, for the 4 adapting CCT, 2700K all the way to 6500K. And then for the stimulus luminance, okay, which is actually the brightness of the iPad, it was actually 200 and 350 candela per square meter. Okay, so you can see that the luminance of these, so the luminance of the stimulus was much brighter than the adapting luminance. Okay, this is what we call the HDR. Then the observer's task was pretty easy. Okay, it adjusts the color appearance of this stimulus to make it as white. So that it means when we compress like the light level in the image processing like pipeline, okay, we can only or we can know that whether we can just compress along the lightness dimension or not. So if the color space was pretty good, so which means that for different lighting conditions, we just need to change the luminance of this patch instead of we need to change the chromaticity at the same time, right? And we look at the result. Okay, so this is actually showing the chromaticities adjusted by the observers to have the patch to appear as white under different conditions. So the dark is actually, okay, so the black point is actually showing when the colors is under the unrelated color. So which means we don't have the surround. Okay, you can see that we have this one and also like the hollow like circle. Okay, like the difference between the two is only talking about the luminance of the stimulus. So it's actually pretty like close to each other. And then if we look at like these green, so these green like data points is actually talking about when the ambient condition was 6500K. And you can see that under the 6500K lighting conditions, so the luminance of the ambient condition doesn't really matter. Okay, you can see that we have 3 different shapes. They actually close to each other. And also like the luminance of the display or the luminance of the square or the stimulus also doesn't matter, right? So they are very close to each other. So which means we have a very good similarity between the black, between the dark condition and also the 6500K condition. Okay, so which means unrelated color is not completely different from the related color, as long as the related color was perceived under 65, under 6500K. But if we are looking at like the other three CCT levels of the ambient conditions, 2700K, you can see that these red dots actually they separate like very like random. Okay, in other words, when the ambient condition was 2700K, the chromaticity will actually change based on the ambient light level and also the luminance of the stimulus. So this also applies to the 3500K. Now for the 5000K, you can see that the difference is much smaller in comparison to the 2700K and also 3500K. Okay, this is actually showing that in this U prime, V prime, like kind of the color space, the luminance and also the chrominance, they are not independent to each other. Now, if we want to make the colors to change its luminance under the ambient condition at 2700K, we have to change its chromaticity at the same time. So of course, this is talking about the U prime, V prime. We don't have any chromatic adaptation. Now we put it into Camo to UCS. Okay, this includes the chromatic adaptation. Now, if it can actually model the chromatic adaptation pretty well, then again, the same color, they should have the chromaticity to be very close to each other and also close to the 0, 0, so which is the adapting condition, right? And you can see that for the 6500K, this is the case. So all the green dots, they are close to each other. But for the red dots, they separated like very random. Okay, so this again says that the Camo to UCS is not so good when the adapting condition was 2700K. Now we calculate the chromaticity difference between the chromaticity adjusted by the observer and also by the adapting condition. Now this can show the results like much clearer. Okay, when the adapting CCT was 6500K, luminance of the condition and also the luminance of the stimulus don't really matter. Okay, we can compress the colors along the lightness dimension. It's pretty good. But now when it is like under 2700K, they really like matters in terms of the luminance of the ambient condition and also the luminance of the stimulus. Okay, but here we are actually talking about the luminance. But most of the time when we do the compression or when we process the image, we are actually talking about the lightness. Okay, we make the comparison between the luminance of the stimulus and also the luminance of the diffuse white. So that's the reason we come back to Camo to UCS again. Now the horizontal axis is actually the J prime, okay? Because the stimulus has a higher luminance than the diffuse white, so that's the reason the J prime value is actually above 100. And this is actually talking about what is happening as an HDR condition. Now you can see that when the condition was 6500K, all the points is actually horizontally like distributed, and they are very close to 0, right? So this means that under such a condition, the lightness dimension is actually perpendicular to the chrominance like plane, which can just change the luminance like independently. But if it's like 2700K, then which means that if we change the luminance, we also need to move the chromaticity. So that's the reason you can see that these lines, they are not very close to 0, and then they are not horizontally distributed. Okay, this is a Camo to UCS for this experiment result for the HDR condition. Now, if we combine with our previous experiment, so this is actually talking about the data points we combine with our 2019 experiments. So which means we have the J prime to be below 100. So the standard SDR condition. So on the left side, these are the refractive colors under the SDR condition. On the right side, so these are the HDR conditions with the J prime to be above 100. And you can see that if the color space is pretty good, then all the data points should actually horizontally like distributed. So which means like this lightness axis is completely independent from the chrominance plane. And also they should be very close to 0. But if that's not the case, so which means that if it's not horizontally distributed, then the lightness and the chrominance, they are not independently to each other. Okay, but if it's not close to 0, so this is talking about the chromatic adaptation problem. So which means when the adapting condition was 6500K, okay, so the independence was pretty good, and also the chromatic adaptation was pretty good. But when the adapting condition was 2700K, then the independence was very bad, and also the chromatic adaptation was also very bad. Okay, this actually tells us about for HDR conditions, the existing color appearance model or the uniform color space is not really doing a good job, especially when the ambient condition was having a lower CGT value. But for the 6500K, which was actually pretty good. Now, based on this, we look at, okay, if like for the Camo to UCS or for the existing color appearance models, for the 6500K, like the lightness and also the chrominance plane was actually independent to each other. But whether this lightness dimension can really predict our perceived lightness or not. or in other words, we are looking at the physical, like the luminance value, and also your perceived lightness. And this is talking about the non-linear relationship between the physical like unit and also our perceptual unit. And in all different color appearance models and also in the uniform color space, we actually have different compression functions. Okay, for example, the CIE-ARB, okay, we all know that we use 1/3 as the power. And then in Camel to UCS, we are using a hyperbolic like function to describe such a non-linearity. But actually, we are not sure whether these functions work pretty well for HDR. And why are we concerned about that? Okay, because if we plot these different color spaces for an SDR condition, okay, this is showing on the left side. So the horizontal axis is showing the white value in comparison to the luminance of the diffuse white. So it's below 100. And you can see that there are some differences in the prediction of the lightness, but actually the difference was not so large. Okay, so we are making a lot of like efforts trying to improve its accuracy, but seriously speaking, we are not making a big differences. But now if we look at HDR conditions, so which means Y over YW is above 100. Now you can see that the higher the luminance of the stimulus, the larger the difference it will be between these different models. And this is the reason we carry out such an experiment trying to see which one is better. Okay, so the experiment was actually still pretty easy. So this is another viewing booth. And then behind the viewing booth, we have two high power LED, so which allows us to change the chromaticity and also the luminance. And we calibrated the system like very, very carefully so that each time the observer will see like the left stimulus and also the right stimulus. And then its task, or the observer's task, will actually to adjust the luminance of the central one to make it appear in the middle. So which means the perceived lightness between area 2 and area 1 should be the same as the perceived lightness between area 1 and area 0. Okay, so that we can actually calculate like different models trying to see whether it can make the good prediction. And we ran this experiment when the adapting condition was 6500K. So this is mainly the reason in the period. So in the previous experiments, we find 6500K. So the lightness like axis was actually pretty good. Okay, we don't need to concern about the chromaticity. Then because we are looking at the HDR condition, okay, we carry out the experiment in the various light levels and also the stimulus light level. Now the lowest like adapting luminance was only 10 nit. And then for area 2, okay, which is the higher like stimulus, so you can see that we go to 33,000 nit. So the contrast or the ratio is kind of like 3,000. Yeah, so the 3,000 like times of the diffuse white. So this is really HDR condition. And then we also go to different like so diffuse white level. But no matter which light level we are looking at, the area 2 was always higher than the diffuse white. So making the scene to appear as HDR. So this is from 10 to 5621 nits of the diffuse white. And then we keep going. We go to the diffuse white, go to 100, so go to 11,000. Again, for this condition, you can see that area 2 was still pretty high. Okay, so this is an HDR condition. And then we look at the result in a very like simple way. Okay, so the horizontal axis is talking about like the lightness of stimulus 2 and stimulus 0. Okay, stimulus 0 was actually a black patch. Okay, you can consider that as the luminance of 0. And then the vertical axis is talking about like the lightness adjusted by the observer, predicted by different models. Okay, so this is using the Y directly. So each figure is showing the result and the one diffuse light level. And you can see that if the model can make very great prediction, then all the data points they actually along, or they should along this 1/2 like ratio line, right? So because 2 plus 0 is actually should be double of the stimulus 1, right? So because this one and this one, the difference is the same as this one and this one. So these two, they add up together should be twice of this one. And you can see that for Y, of course, this is not so good. Okay, so we have these different light levels, and this is the combined. Okay, I'm only showing part of the result here. So you can see this is not so good for the luminance. Then we look at the HDR CIE-ARB. So this was actually developed by RIT. And again, you can see that the data point is not along the 1/2 like the ratio line. Okay, even you combine them together, it's not good. Okay, so because this is not making the right prediction as we do in the HDR condition. And then this is the ICT-CP, okay, which is claiming to do for the HDR. But again, you can see it is not so good, okay, because ICT-CP is mainly looking at the threshold instead of like the appearance. And this is camel to UCS. Okay, camel to UCS was pretty good for SDR, but not for HDR. Again, the data points is not along the 1/2 line. Okay, and then interestingly speaking, we find CIE-ARB was actually making a very good performance. Okay, because CIE-ARB is using a power function, and you can see that all the data points, although it's not perfect, but they are very close to the 1/2, the diagonal line. And then also for the IPT space, you can see that it's also pretty good. And then the same thing happened for CIE-ARB and IPT is they are using the power function to describe the nonlinear like compression. So which means for HDR conditions, maybe we should come back to the power function instead of the parabolic like function. Okay. And then, so this is talking about the luminance. And after the luminance compression, we always concern about the chroma compression. So the chroma compression or the adjustment needs to be made on the color space that has very good hue constancy. So which means that you are only adjusting the chroma, but you are maintaining the same hue. Okay, for example, for this red shirt, so very obviously it's it's out of the gamut. Okay, it's too saturated. You need to compress the chroma levels, but you have to maintain its color as red. And the famous or kind of the well-known phenomenon is CIE-ARB is not so good for the blue color, and we did find that. Okay, so this is the blue bar, and then if we compress that along the CIE-ARB hue, so you can see that it will shift to the violet or the purple. And we also find that along the CIE-ARB, like another serious problem is kind of the orange color. Okay, so for red, you compress to the center, so it will actually shift towards the orange. And this is also the problem like noticed by many like smartphone companies. So red and also the blue is the most serious problems in the existing color space. And in order to look at how we should perform such a chroma compression for the constant hue, we actually run another experiment and trying to look at for close to the RAC 2020 gamut, how different color spaces they are actually perform for the hue constancy. And then so I just show the result here. Okay, so each line is showing the same perceived hue. So if the color space is pretty good, then all the lines should be a vertical line go to the origin. And then you can see that CIE-ARB is not so good. So for this line, this is the blue color. Okay, this is what we know. And then for the red, okay, you also see it's not a straight line. Okay, and then in comparison to CIE-ARB, and you can notice that we look at different spaces. Like on average, you can consider that IPT is kind of like better. And also for the ICTCP is kind of the better, but for others, none of them, they are pretty well. Okay, especially if you do the job in the YCBCR, it has very serious problems. And this actually matched to what we expected, like based on our observations for the image processing. And if we have these constant hue locus or the constant hue loci, we can actually do the chroma compression to have very good performance. Okay, I just show some of the results. Okay, so the right image is always showing it's the original like condition, and you can see the colors are actually oversaturated. So because they are out of the gamut, and then the left image is showing the result if we make the compression in the CIE-ARB. And for this image, you can see that it's the blue kind of the light, and if you compress that, it will shift to the purple or shift to the violet. And similar thing happened to the ceiling color here. And this one is if we map in the CIE-ARB and then we correct the hue based on our result, and you can see that we can correct the colors to be very well. Okay, so which means that our experimental results can show the color, can show the hue correction pretty well. Okay, this is for this image. And similarly, for this image, okay, you can see that this is out of the gamut, and that's the reason. So you see it's kind of like pink colors, but if you make the right correction, so this is actually a blue color. Okay, and then also for this one, you can see that it is the blue light, but actually the reflection on the human being's face is kind of the pink. But if we just compress that in the CIE-ARB, now you still have the pink face. But if we make the correction, so you can see that the face is becoming blue. Okay, so this means that we are actually doing some good job trying to make the color space to be more uniform in terms of the constant hue. So based on these three experiments, so we find that the existing models, they have some problems for the HDR and also for the white color gamut conditions from different perspectives in terms of the so in terms of like whether the lightness dimension is perpendicular to the chrominess plane, and whether so we have a very good function to describe the relationship between the physical like intensity and also our perceived lightness, and also for the constant hue when we do the chroma compression or the gamut compression. Okay, so these are the things we actually have some problems at this moment, and we need to make more efforts trying to improve that. Now, to conclude all my talk, okay, we for the color scientists, we actually made a lot of great efforts, and then we are doing a lot of like great job to help the industry to solve the problems. But actually, because we have new technologies, we need more work for the color science, okay, for color appearance models, for uniform color space, and also for the fundamental color matching functions. But for these modern technologies, we have these challenges, but we also have more and more good opportunities, trying to have better and better cross-media color reproduction, and then to provide better user experience. Okay, I think that's all I want to present today. All right, thank you.
Thank you very much, Tommy. So everybody got any question? I think Tommy just gave an excellent presentation to introduce current challenge for the color imaging reproduction in general, but clearly there are some problems.
Yeah, I don't have a question as such, Tommy. I just want to say congratulations. You know, that's a huge amount of work you've shown us today.
Thanks.
Very, very impressive. The only thing I did want to mention was, was I right in thinking when you looked at the loci of constant hue, C-Lab wasn't too bad? Is that fair to say?
Well, for the blue and also for kind of the red colors, it was pretty bad. But for the green and yellow colors, like these are fine.
Yeah. Which would you say is the best one there?
It's kind of I think ICT-CP was actually pretty good, and also for the IPT. Well, like basically like these two are kind of the so the similar like the fundamental things.
Okay, thank you.
I think most of the so in practice we still use C-Lab pretty like often, so because it's pretty simple. But I think like we actually developed like these curve or these like constant hue like locus, and we can apply some lookup table at the end. So for these, so we make the map like in the CIE area, and then we just apply like the lookup table at the end, and we can have pretty good like performance here.
I know there's a rotation term in, I think, CIE DE 2000, especially in the blue region. I wonder if this is. Okay. I wonder if this is to do with that problem in the blue region of hues not being constant.
I'm not sure. Yeah, I didn't look at that problem. Yeah.
It might be related.
Yeah, could be.
There was a question in the chat I noticed. By Rafa Hertaz. Says, what about CAM16?
I think they are the same. Okay, so yeah, so for this experiment we did not look at CAM16, but for the non-linear compression we also look at. So we also look at CAM16. Actually, no big improvement, and to my knowledge, CAM16 only makes some change on the mathematical calculations, because so it's actually like the mass. So the mass problem, like in the CAMO2, it's not really including more data sets, or it's not really including like better data sets on more viewing conditions. So I don't think CAM16 will make the big differences here.
Tommy, so from your presentation, I can say what you found it's very interesting. It's when we look at the HDR, when we look at the wide gamma display, and your conclusion is current reproduction might not work very well, right?
Yeah.
On the other hand, you also talk about when we look at in our daily life, what we say actually it's much lighter and much wider than the display color.
Yeah.
So then my question is, in your opinion, do you think theoretically or potentially we could do much better color reproduction when we use HDR or wide color gamut.
I think so. Yeah. So I did not show the slides here. Okay. So we have these experimental results. So in terms of the nonlinear compression and also in terms of the chroma compression, and we get the raw image from iPhone, and then we make the adjustment based on our experimental results and compare the results to the iPhone image. We can actually make the colors appear much better in comparison what to iPhone is doing. So of course, that's everything we do is purposely designed for the setup. But if you want to put it in the in the iPhone or in the smart devices, they actually need to do a lot of estimations and interpolations. So that's the difficulty. It is there. But I think if we have the setup in the lab and actually by using all the experimental results, we can do a better job.
Okay, so potentially we could do a better job.
Yeah.
And then the question is, you already did some preliminary results for the color matching, that is in cone level. Also, it might involving color appearance model, also color difference evaluation. So do you say if we want to solve the problem completely, then we need developing everything new or anything we can use from previous study?
No, I think in terms of the color science, most of the things we do is pretty kind of empirical. So we just want to get more data and then to try to revise the model to focus or to include more different viewing conditions. So we don't need to start from the scratch, but we just want to include more data and then to build models to cover more different conditions. And then, that's better.
Okay, so then my last question is not exactly to do your presentation, but that is my interest, something I'm interested. It's about the blue light, right? When the display become lighter and lighter, and it's go to HDR, and the blue light is stronger and stronger, do you think potentially that's not good for human health?
I think it's still fine. Okay, so if you compare the amount of the radiation we have from display to sunlight or to daylight, it's actually the intensity is much lower in comparison to daylight. If we don't have any problem in the daylight, I don't think we will have the problem for display. And also we talk about HDR display, we're actually not talking about to make the entire display to be brighter. For HDR, we just want to make a couple pixels, or we want to make small regions to be brighter. And if we have that kind of the perspective, I don't think it will cause a problem to the human health.
Okay.
All right, thank you.